Okay, so before I start, so let me just remark on this issue of the dimensions. So remember yesterday I mentioned, so for example, for this phi4 equation, which was of this dt4 equal Laplacian phi, basically minus phi cube plus space-time white noise. So I mentioned that we can give a meaning to this equation as long as the space dimension is strictly less than 4. And so now let me just show you what happens in dimension. So why is dimension 4 somehow special here? Okay. Well, so remember that the space-time white noise, we saw that it essentially scales, or it belongs to these C alpha spaces for alpha less than minus dimension over 2 minus 1, right? And then because of Schauder, we concluded from that the solution itself...
Was it plus 5 as well?
Yeah, well, okay. So yeah, it's included in the definition of the cube. So then the solution we've seen is in these C alpha spaces for 2 better, so that will be 1 minus dimension over 2. And as soon as dimension is bigger than 2, this is negative, right? And then what we've seen is that the phi cube, well, locally the worst term in some sense in terms of its behavior is basically it behaves like the solution to the linear equation cubed. And then, well, what we did yesterday is we saw, well, the cube doesn't really make sense, but you can make sense of this Wick cube where you sort of stick it into the third Hermite polynomial with the correct parameter. And then the correlation function, the covariance that you get for this object is just the cube of the covariance function of the linearized object, right? So that's how these Wick powers work. And so in terms of, if you want to say if you have something Gaussian or something which has very light tails, being in a somehow C alpha space for negative alpha basically means that your covariance behaves like sort of x minus y to the power minus 2 alpha. Okay? And so if the covariance just gets cubed, well, it basically means that the alpha gets multiplied by 3, right? So what you expect, right? So it's different from the positive values of alpha, right? So if you have 2 Hölder functions and you multiply them, then of course the regularity is just the minimum of the 2. But if they have negative regularity, then what you expect is that the regularity of the product is in some sense the sum of the 2, which is worse than the minimum of the 2 if both are negative, right? Of course, in general, you're not allowed to do that, but somehow when it makes sense, that's the rule of thumb. And so what you would get here is 3 minus 3d over 2, right? And now, what happens in dimension 4? Well, dimension 4 is exactly the dimension where this number is equal to this number, right? So you see, if I want to make these two equal, you get exactly 4 equal to 3d over 2 minus d over 2, which is just d, right? So in dimension 4, these two numbers are equal, okay? And so what, in particular, if you're in dimension greater than 4, then this number starts to be more negative than this number, right? And so that tells you that sort of the heuristic that locally the solution to this should just look like the linearized equation, that heuristic breaks down, right? Because if you start from that heuristic, you would conclude that this guy has this regularity here, which is actually worse than the regularity of white noise, and therefore the solution itself should actually not be in C alpha, which is that guy plus 2, but it should be that guy plus 2, which is the worst guy. But then it's even worse, and then that guy gets even worse, etc. And you sort of go down to minus infinity, and sort of in some sense the heuristic doesn't close, right? And so that's, similar things happen with the other examples that I showed you, right? So in the KPZ equation, it's at dimension 2 that, this starts to break down. And for this parabolic Anderson model, it's again in dimension 4 that it breaks down, etc. Okay. So this is somehow where, there's a power counting involved here, which tells you whether these heuristics have any chance at all of working or not, right? So whenever this power counting works out, I would say that, the equation is subcritical. So being critical would be the one where the two powers are equal, and supercritical would be sort of, the one where it goes the other way around, where the nonlinear term behaves worse than the noise term. And so the techniques that I, want to present to you, so they work in the subcritical case. Okay? So all the examples that I wrote down yesterday, they are subcritical. But of course, subcritical doesn't mean, it depends. The critical doesn't really have a very good definition in this business, right? So it's not, there's also a critical value at which, you start to have problems defining the equation, and here it would be dimension 2. But in some sense, the real sort of critical dimension here is 4. And this is, of course, also known from the Ising model, right? So if you take a Ising model in dimensions bigger than 4, you somehow know that even a critical Ising, the magnetic field sort of behaves Gaussian in a Gaussian way at large scales, and this is not true in dimension less than 4. Okay, so there's really, and this is supposed to be in the universality class of the Ising model, so there really is a difference in behavior at dimension 4, right? So you sort of, the fact that it only works for dimensions less than 4 is not the restriction of the technique, it's because these objects really start to behave in a different way at dimension 4 here.
But usually D larger than 4 is considered much simpler.
That's the thing, and so it's simple. The reason why it's simpler is because what you then get is the behavior should just be this, right? So in some sense, what you do is if you want to get a limit, you basically have to rescale it in such a way that in the limit you would just get the heat equation, but it's subtle, so in the sense that, so if you wanted to prove a theorem along the lines of, regularize this and then let epsilon go to 0 and you would converge to the heat equation, that wouldn't be true with sort of this scaling. So you'd have to scale things differently, and then the white noise would really be kind of generated by the nonlinearity. So it's not a strong kind of convergence, right? But in law, you would expect, so I don't think that this is a theorem, but certainly the expectation is that if you rescale this in the correct way, then in dimension bigger than 4, this would just converge to something Gaussian. So at the level of the corresponding invariant measures, well, in dimension 4, this is basically the content of this long series of papers by Bauer-Schmidt, Slade, and Bridges that were put on the archive a couple of years ago, where they basically take a sort of discretization of this on a grid, look at the invariant measure that you get, and show that in dimension equal to 4, if you perform the correct, power of a logarithm correction in front of this, then the large-scale behavior is indeed Gaussian. Okay? And if it's dimension strictly bigger than 4, the same thing is true, and those essentially proved by Fröhlich and Eisenman back in the days. Okay, so in dimensions greater or equal to 4, in some sense, from a SPD point of view, things are not so interesting because the limiting object that you expect to get is just Gaussian. Of course, it might be very difficult to prove that, but there's a clear conjecture as to what the limiting object should be somehow, right? Whereas in dimensions less than 4, here there's, the solution to this equation is a non-Gaussian object, which you cannot describe it other than a solution to some fixed point problem. Okay, and the point of these lectures is to explain how to set up this fixed point problem. Okay, so this is about this subcritical case, and now let me just remind you for a second. Let me just give you a slightly different perspective on the calculation we did yesterday. Right, so what we did yesterday, we added this linear term. We added a term constant depending on epsilon times phi. And then we rewrote the equation as sum of the linearized equation plus a remainder, and we regrouped terms in the equation for the remainder to then get something well posed, okay? So now let me sort of essentially redo the same calculation, but in a slightly different way, and to give a different perspective on this. I'm going to actually use slightly different notation. I'm going to use some graphical notation now. So I'm going to, so the psi, I'm going to write it as basically a little circle, and convolution with the heat kernel, I'm going to write it as a straight line. Okay, and with the convention that, you know, composing things just means putting them on top of each other, and multiplying things means just, so you're going to obtain trees in that way, and multiplying things is just sort of joining the roots. So here the solution to the linear equation would just be, so the one that I called V yesterday, well, V is obtained by just convolving the noise with the heat kernel, and therefore I would just write it like this, right? And so our ansatz, the ansatz that we had yesterday was that we just wrote phi equal to the solution to the linear equation plus a remainder. So now let me call the remainder little phi. So that's the one we called u yesterday. Okay. And then what we see is that this right-hand side, right, so this phi cubed term, well, is given by, well, if we write it like this, so this is just given by, well, I expand the cube, right? So there's this term cubed, which now I write like this. Then you would have a 3 phi times this term here. You get a 3 phi square times this guy, and then you get a phi cube. Right? And then what we saw yesterday is that this guy here, of course, if you simply take the solution to the linear equation and you cube it, this doesn't converge. Okay? But then, now what I could do is I could say, well, in order to make this guy converge, I actually reinterpret this as being the Wick cube instead of the normal cube. And I reinterpret this as being the Wick square instead of the normal square. Okay, so I say, so now, if you want, I could also, maybe the way of interpreting these symbols is instead of directly identifying a symbol with a stochastic process, I could also view the symbols as just symbols and define a map, say pi that takes a symbol. So this is going to be a boldface pi. There's going to be a non-boldface pi later. So I have a map that takes a symbol and turns it into a stochastic process. Okay, so then here it's really more like this. And so now I could just redefine this map, okay, in such a way that, you know, this guy, for example, is just the Wick square of, so sometimes people write it like this, right? So it's the Wick square of the process V instead of just the usual square of the process V. And, you know, for this guy here, I could define the map boldface pi in such a way that it just spits out the Wick cube. And then what we've seen yesterday is that actually, so if we redefine the map boldface pi in this way, so then we have two things. So the first thing is that, well, regularizations, sort of epsilon regularizations of these objects do converge to a limit. Okay. And the limit is in some nice C alpha space. It is actually in every C alpha space for negative alpha. And then the solution to the equation with this right-hand side is perfectly well posed. Okay, it's perfectly well posed, and it's continuous as a function of these ingredients. Okay? So the perspective that I could take now is to say simply I view the solution map as a map that takes as my ingredients not just this, not psi, but it actually takes as my ingredients the v, the Wick square of v, and the Wick cube of v. Right? So I could just pretend that I don't know anymore that this guy was actually built from this guy by taking a Wick square. I could just take it as a completely independent guy. And then I have a perfectly nice solution map that just takes as an input this guy here, and this guy here. And it spits out the solution to the equation with this right-hand side. Right? And what we saw yesterday is that if we make the particular choice of putting here the Wick square and here the Wick cube, then it turns out that the solution we get in this way is actually related to the solution to the original equation, provided that we modify the equation by adding a term like that. Right? We saw that if we modify the equation, then that's equivalent to, in some sense, looking at the original unmodified equation and modifying the definition of these terms. Right? So that's what we saw yesterday. So there are two ways of interpreting this. And so that's something that we're going to really make use of. So the philosophy now, oops. Okay, so the philosophy now is going to take to do the following, right? So you start, so say you look at a class of equations. So here the class of equations that we could look at is the class of all equations of this type for different values of the constant c here, okay? So we have some class of equations, say f. So this is some class of equations. And so in this particular case, I could identify this with R because there's just one real parameter that describes the elements in my class. But in more general cases, they could be described by more than one constant or even by a bunch of nonlinear functions, right? Like in the case of this geometric stochastic heat equation, then my class of equations, the input here would be maybe the Christoffel symbols and these vector fields sigma or something like this, right? So it could, depending on the situation, this could be something quite small, like just R. It could be an Rn, or it could be a quite a bit larger space. And so then, the naive notion of solution, where you just regularize the noise, gives you just a map which takes an element of your class of equation. It takes a realization of your noise. So say for fixed epsilon, that would be just a smooth function. Right? So here you think of the psi epsilon as being an element of just some c infinity, say, or ck for k big enough. And then maybe you need an initial condition because you look at an initial value problem, but the initial condition is not going to play an enormous role, so I forget about it. And then you get a solution. So the solution will live in, maybe you view it as an element in some C alpha space, so that's my solution. Okay? Phi, which now depends on the specific equation I'm looking at, so the value of the constant C, and the realization of the noise, right? So now the philosophy is we're going to basically factor this map as a composition of two maps, right? So the first one, so that would be the analog of the map here that takes the realization of the noise and it builds both V and this guy here, this Wick square and the Wick cube, right? So it builds this additional data from my noise. Okay, so here we have some map that goes to some different space, so let's call it M for the moment. So in this example, M would just be, some C alpha space times a C alpha space times some other third copy of a C alpha space. Okay, so an element here would just be this data. Okay. And then again, right, for every equation in my class, well, I have a natural way of right? I can rewrite it in this way. Okay. And then I can solve the equation. I can solve this equation here, so the equation with this right-hand side, where I just replace these three guys by the three pieces of data that I've constructed here, right? And so that gives me some kind of solution map, which is also going to be some sort of element of C alpha. Okay? Now, in the specific case where I obtain this data by simply taking the usual square and the usual cube, then this diagram commutes. Right? So it's completely equivalent. Solving this equation or solving this equation is completely equivalent if this guy is the actual square of v and this guy is the actual cube of v. Right? So then this commutes. Now, what we actually did yesterday is what we saw is that, well, in this particular case, it's not a good idea to define this guy as the actual square and this guy as the actual cube. You should rather define this guy as the square minus C epsilon over 3, and you should define this guy as the cube minus C epsilon times V itself. And if you do that, then these actually converge to a limit. Okay? So here, well, in this example, there's a natural. So here there's actually an action of R, the real numbers with addition viewed as a group. Okay? So there's an action of the real numbers onto this, which all it does is it somehow turns, you know, usual products into weak products. Okay, so in some sense the element of R here would be your C epsilon, and you can see that actually, you know, sort of these turning powers into weak powers, it does actually have the properties of a group action. So if you take somehow, if you do this operation of twice, then it's the same as somehow doing it with the sum of the two constants. Okay, so it is actually a group action.
Is it R just because the family was consisting of one parameter? Family of it's always R.
No, so it's not always R, and yes, it is related to somehow how big this family is, but it's built in a different way, a priori. Okay, so yeah, so it would not always just be R. So in general, there might be more than one constant showing up, right? So it doesn't need to be just one constant, and so the philosophy will be try to build here some group. So let's write, well, usually write Gothic R, but I don't know how to write a Gothic R on the blackboard. So let me write some sort of curly R here. Okay, so you want to build some kind of group which acts on that space here, and you know the point of the action being that you can find elements of the group that makes this thing converge. Okay, so like here, well, we found values of the constant, so that if we replace the square here by a weak square and the cube by a weak cube for these constants, then these elements actually converged, right? Sorry?
Is it clear it's always a group? Because
it's not clear a priori, but I'm going to give, well, you won't be here anymore, but there is a general construction, and the construction gives you a group, actually. Yeah. It's not.
in this case, when you do the big products, it's because you subtract linear terms. That's why it's more.
Well. Well, no, so here it just acts in a rather trivial way, right? I mean, so the way it acts, so C would map, right? So there's V2, which would be somehow the square, and there's V3, right? And the way it acts on it would map V on itself. It would map V2 onto V2 minus C times 1 somehow. and it would map V3 into V3 minus 3C times V.
So that's
right?
Because it's linear in C that you get.
And so here it's linear in C. But okay, so in general it will not always be linear, but it will always be somehow polynomial. And it will have a group, it will have a group action structure, but it will not always be linear actually. Yeah, linear in that sense. And so the group here is in general, it's not necessarily just some RD with additive structure. Okay, so because you can have products or powers of these constants showing up. Okay, and so now. So what we see, of course, what we saw yesterday is, what you see obviously is that now, if you change the definition of the V square and the V cube up here, and then you solve this equation here, now of course the solution that you get is no longer the same as what you get by just solving this, right? So now the diagram in a way doesn't commute. I mean, if you go up here and then modify the thing and then you go here, that's not the same as just going here. But it is actually the same as modifying, looking at a different equation, which is the equation where you add this term C times phi here, right? And so you can find a modified equation so that if you solve the modified equation, that's the same as formally solving up here the unmodified equation, but with this modified element, right? So that's what we saw yesterday, is that adding this term C is equivalent to somehow looking at formally the equation where you haven't added anything, but modifying the definition of these guys. Okay? And so here in this case, well, my group, which is just R with addition, it also acts on the class of equation, and it acts in a trivial way by simply adding C to that constant here. Or maybe 3 times C if I write it in this way, or C over 3 or something like that. Okay, so it acts simply on the right-hand side in such a way that then, if you take the same group element here and here, the diagram commutes again. Okay, so you have the same group here that acts on this piece of data here, and it also acts on the class of equations that you're considering. Okay, and so this is the general philosophy, if you want, that we want to follow, right? So the general philosophy is you factorize your solution map into sort of a composition of two maps in such a way that first you have this group that acts on both of these factors in such a way that the thing commutes. The group is big enough to actually contain enough elements so that when you take some regularized version of your noise, you lift it up here, and then you act on it with that group, you can find elements to make this converge to a non-trivial limit. And then furthermore, you can do this construction in such a way that this map here is continuous in some natural topology. Okay. And it's a topology which is somehow good enough, if you want. Right, so what's the analog here? So the analog here is that if we just take, right, we just view the noise as being an element of C, somehow minus 3/2 or minus 3/2 minus, then this solution map is not continuous in this topology. Right, that's the whole problem. However, up here, the natural topology is to put these kind of C alpha norms on these guys for just some very small negative alpha. Okay, and so that's a much stronger topology. And so if you have a stronger topology on the source space, it's sort of easier to be continuous. And so this map is actually continuous, right? If you take the alpha not too negative. Okay, so we've taken this discontinuous map and we factored it into something times something continuous. So obviously this is also discontinuous, right? So if you take a general element in C minus 3/2, you're not allowed to take its square. Right? So this map here is certainly not continuous in general. But then here is sort of the probabilistic part of the construction is find a canonical way of building this map in a way which is somehow measurable, right? So here you view this actually as some kind of probability space, so you have the probability space on which your noise lives, and then you can realize this actually as a perfectly reasonable measurable map, which is just not continuous, but which will happen to, okay. So it turns out that there's actually a rather canonical construction of this composition, which turns out to be somehow continuous in law in a certain way. Okay, so even though it's not continuous in a pathwise sense, so if in law, under sort of reasonable assumptions of what you get down here, in law you can actually make this bit, sort of this composition, you can make that sort of continuous in law, even though these two factors would themselves not be continuous at all in any sense at all. Okay? Right. So now, what I want to tell you is I want to give you an idea of how, what this space is. Yes.
And so the group acting downstairs in F
would be the same. It would be the same. It's the same. Right. So that's the point. Yes. Thanks. Right. So the point is that you want the same group acting on both sides, so that it restores the commutativity of this diagram, right? So in the sense that if you take the same element here and here, then this again kind of commutes.
And if you have different ways upstairs to renormalize your things so that they converge, how do you choose one canonically? You say that R is big enough.
Right. So okay. So in some sense, this arrow should really be viewed in this way, right? So somehow you start with the shape of your equation, which is the one without the C epsilon, right? Then here you just take the identity, but you act on it with this, which gives you something else, and then this should be the same as somehow this. Right? Yeah. So what? Sorry, I interrupted you. So what did you?
If you have different ways to normalize things, how do you choose one?
Yes. So that's a very good point. So indeed, so in general, the way to renormalize things here would not be unique, right? So just like here, I mean, actually, if one specific choice of C epsilon works, now of course C epsilon plus 1 works as well, right? So the choice here of this renormalization is not unique, and so what you get in the limit. In general, with different renormalizations, you would get different limits. And so you have a family of limits, which is parameterized by that group R, right? So in some sense, the possible limits that you get is not, just one point, but it's a whole family of limits parameterized by that group R. And so it's quite important that, so this family of limits, so say if R is just the real numbers, no element here is canonical in the sense that, so you can have a one-dimensional family of limits that's parameterized by the real numbers, but the parametrization itself is not canonical, right? So you cannot say somehow the element with value equals 0 is somehow my canonical element, because the parametrization itself is not canonical, right? So it's like sort of a cartoon is you would have sort of that's for epsilon non-zero, right? So you have a family of, here you also have a family of equations parameterized by that element, which is, you just take the equation you start with, and then you look at all the ways of acting with R on it, right? So you have also a one-parameter family, and then as a one-parameter family of solutions, in the space of solutions, you have this convergence of the one-parameter family to a limiting one-parameter family, but the parametrization doesn't converge. Okay, so the one-parameter family converges, but if you take somehow one fixed value of C, then in some sense that would just sort of run out to infinity, and you have to pull it back in order to see something non-trivial. Right? So if you want to actually converge here to some point here, well, you have to look at different. Right? If you want to take the same guy here, then you have to take different guys here in order to get a limit. And this procedure is not completely canonical in the sense that you know, different ways of approximating psi would give you different elements here. And so all you can say is that they would always, you always converge. Right? So there is a canonical, okay, so there is basically a canonical way of choosing this, but it's still not, it relies on some cutoff somewhere, and it depends on the choice of cutoff still. And so at the end of the day, you just don't have a canonical parameterization of it. And so it's in some sense, in some situations you do, because in some situations you might have formally a symmetry in your equation, right? And then you would have, these guys could break that symmetry, right? And then you would say, well, okay, so canonically I want to actually just take guys which don't break the symmetry. And then maybe that makes it small enough so that there's nothing left. So for example, if you take in the particular case of just stochastic differential equations, you have exactly the same picture. And this here would be also the real numbers. And that would be the thing that changes you from sort of Ito to Stratonovich, etc. Right? And so then you could say, well, you know, is the canonical one Ito or is it Stratonovich and so on, right? So it depends a little bit on what you want, what properties you want. Right? So for example, you could say, oh, I have a kind of symmetry which is invariance on the changes of coordinates if I want to have a sort of geometric picture. And then you see that, well, there's actually only one element which preserves this, and that would then give you the Stratonovich solution, right? But on the other hand, there's also a canonical way of choosing these things which sort of recenters things in probability space, and that would actually then give you Ito. Okay, so actually both of them show up naturally also here. Okay. So in the remaining 50 minutes or so, I want to give you some idea of what this space actually is, you know, in the more general sense. So the important thing, so in this example, this space was itself again just a linear space, right? So it was just this triple v square v cube, and you could just take it as C alpha times C alpha times C alpha for suitable value of alpha, and so it was kind of a nice Banach space. So in general, you cannot take this thing to be a linear space. Okay? So in general, you actually have to, this big space here is going to be something nonlinear. And so the example on which I want to show you what's happening is that example of this geometric stochastic heat equation. Right? So remember this geometric stochastic heat equation. So that was this equation for these loops taking values in a manifold, and in local coordinate charts, the equation was given by something like this: dxh beta, dxh gamma plus sigma I alpha of h psi I. Okay, so that was the equation in local coordinates, where these guys are Christoffel symbols, and that's a collection of vector fields that generate the metric. And now you see, so if you want to treat this, so you know, let's try to do something like, you know, this the Prato-de-Bush business. And so here you see that you're kind of stuck from the beginning, because I mean H is supposed to take values in a manifold. Your manifold, there's no way of adding elements in your manifold, okay? So I just cannot write H as a sum of two things, right? It doesn't even make any sense, because in a manifold I can't add things, okay? And so I'm already stuck at step number 0, right? So I cannot expect to have any sort of global decomposition like this. Okay? However, what I want to do is something a little bit similar, but do it locally instead of globally. Right? And so what do I mean by this? Well, here, you know, if I use the same notation as before, so I'll also use little circle for the noise, and I'll use this for convolution with the heat kernel. This time, because there are also derivatives of the solution showing up, it will be convenient to also have a notation for convolution with derivative of the heat kernel. Right? And so here I'm going to use just a wiggly line instead of a straight line. Okay, so it's just a notation. So then here again you would expect that locally your solution near a point looks basically like the solution to the linear equation, but this time it's actually the linearized equation around the point where you are, where you would have to replace this here by the value of h at that point. Right? So here it's now more natural to say, well, near, you would want to say that near some point z, well, h alpha, basically behaves like sigma alpha I of h times, the ith, well, here it would be sort of the ith guy, the ith linearized guy. Okay, so the same as here, but well, now the psi has more than one component, so it's the one with psi I, right? So you expect that you have something somehow like this. But now what does this mean? Because here you have actually the h itself that kind of appears in here, right? And so the correct way of viewing this is to say that it's really, but we're not talking here about the values of h, right? The values of h, they will be whatever they are, and it's really just about the local behavior, right? So you don't expect the value of h to be in any sense related to the value of this guy, right? Because that already, as I said, it doesn't make sense on the manifold. You can't add things and so on. But what you do expect is that somehow the small fluctuations around a given point for this guy would look like the small fluctuations of this guy around the same point. Okay, so this is what you would expect. So the way of interpreting things here is to say, well, what you expect is that if you take a point z, which is close to some fixed point z0, so these are space-time points, right? Then you would expect h alpha of z to be well approximated by h alpha of z0 plus this guy evaluated on z0 times, well, here it would be now it would be this guy, if you want, evaluated on z minus the same guy but evaluated on z0. Right? So you would expect something like this. Right? So it's somehow, it just says that locally the value of h near z0 is given by, well, its value at z0, and then plus, well, some little fluctuation, and that little fluctuation should basically, to highest order, it should look like the corresponding little fluctuation of the equation where you simply replace this guy by its value at z0. Right? So that's kind of it's a reasonable thing to assume somehow, or it's a reasonable thing to expect. Right? And so I'm going to rewrite this as saying, well, now this guy here, right? So now you see this is no longer just a function of z, but it actually depends. I have to recenter things in a way which depends on the point around which I look. Okay, so now let me call this just pi z of this guy here, right? And that's just a definition. Okay, but pi z0. Okay, so pi z0 of z, right? So I think of z0 as being fixed and of z as somehow varying in a very small neighborhood around the point z0. Okay? And so then I expect to have an expansion of the type, right? So let me just rewrite this. I expect to have an expansion of the type h alpha of z0 times, if you want, the constant function 1 plus this sigma I alpha of h of z0 times this function here, right? So in the sense, if I define a function by taking values formally into simply linear combinations of these symbols, okay, so then I expect, so now so what we expect is that we expect that the h itself of z is somehow well approximated by pi z of by z0 of this h alpha of z0 as a function of z. Okay, so if I just this map pi z, by definition pi z of 1 would just be the constant function 1. Okay, pi z of this symbol would be this increment here. Okay, where z0 is fixed, and I view this as a function of z. And then this identity here can be rewritten as, in this particular way, if I define the capital H somehow like this. Okay, so this is really just notation, if you want. But it says, well, since this here sort of encodes the small-scale behavior of, or the expected small-scale behavior of my solution around a given point. Okay? And now the hope is that if you describe the small-scale behavior to sufficiently high order, okay, then that gives you enough information to somehow uniquely describe the right-hand side of your equation in a way which is somewhat similar to what we had here. Okay, so we would like to have some sort of ansatz for the solution, except that here the ansatz is local instead of global. And then we would like to say, well, if you take any function that somehow satisfies this ansatz, then this should give me enough information in order to actually be able to define in a sort of unique way the right-hand side of the equation, provided that I have a definition for all of the analogs of these objects here. Okay? So now, in this particular example, well, it turns out, you see, so each of these objects comes in a very natural way with a degree. Okay? So 1 very naturally has degree 0. Okay. This guy, well, what's the natural degree? This guy had naturally degree, so here we're in space dimension 1, so it had naturally degree minus dimension over 2 minus 1, which would be minus 3/2 in dimension 1. And this operation of convolution with the heat kernel naturally has degree 2. Right? We've seen yesterday that you somehow improve regularity by 2 when you take convolution with the heat kernel by these Schade estimates. So this here has naturally degree 1/2. Okay, so there's a natural notion of degree here. And it turns out that here, in order to close this argument, you have to describe the solution not just up to degree 1/2, but actually up to degree 3/2. Okay, so I give you just to give you an idea of what this looks like. So if you take, this ansatz and you push it up to degree 3/2, you get something like this. Right? So the first two terms up here, that was this ansatz, right? Where I simply removed all the indices so that otherwise you have indices all over the place. If you remove all the indices, you have the first two terms would be this ansatz here. If you go up to degree 3/2, well, you have a whole bunch of other terms that start to show up. And so here you see that you have straight lines and wiggly lines that somehow correspond to heat kernel and derivative of the heat kernel. And if you do a similar sort of degree counting where the heat kernel counts as 2, derivative of the heat kernel counts as 1, noise counts as minus 3/2, then you see that, well, that guy has degree 1/2. These two guys have degree 1. This would just be somehow the linear, would be like a slope, like a derivative, has degree 1, and all these guys have degree 3/2. And then there's nothing else that has degree 3/2. Okay? So in some sense, the data. So what would be the data that we need, right? So the data that we need now, instead of being just v squared, and v cubed, like in this simple case where we had these three guys, now the data that we need is somehow all of these guys here, but that's actually just the guys needed to describe the solution itself. Right? So here, in order to describe the solution itself, the only guy we needed was that one. Right? And the other two guys appeared in the right-hand side of the equation. Okay, so then if you do the same thing and you look at the guys that appear in the right-hand side, well, you have, I don't know, 50 of them or something like this. I mean, you end up with some ridiculous number of these little symbols. But the claim here is that now we can put, there's a natural topology you can put on, right? So you have so you put a topology, if you want, on these maps, boldface pi. So the maps that turn each of these symbols into an actual function, okay, or a distribution. Now you can put a topology on these guys, and then that would be this space M. Okay, so the space M would be the space of all the maps pi, or actually, rather these maps pi z for every value of z, for all of the symbols that appear when you look at both, you know, the solution and the right-hand side of the equation. Okay? And now, so now here, of course, you can't really do things by hand anymore, right? So here we could just show by hand that these two guys, if you make the right choice of constants, if you modify them with the right choice of constants, then we make them converge to a limit. And, well, the effect of modifying them by a constant had the same effect as simply modifying the equation. Okay? So the claim is that the same thing is still true here. But of course, there's no hope to be able to just do it by hand. Right? So you have to have some kind of a machinery that tells you that this always works. Okay, you cannot just check it anymore because there's too many things to check. Yeah?
Where is the analogous of the constant that we were playing with on that blackboard there?
Right, so we haven't seen, right, so the analog of this constant here, right. Okay, so in this particular case, the analog of that constant would be that if you want to make these guys converge, then you actually have to modify this equation by some, you know, so you have some kind of C epsilon j's times some fj alphas of h. So you basically pick up a bunch of vector fields that somehow modify your equation with constants out in front, and these constants in principle diverge. Now it happens that because of geometry, there are magic cancellations. So here, the natural thing is to not take these two guys completely independent, but to choose a metric and then take here vector fields that generate the metric, and here Christoffel symbols for that metric. Okay? So these two guys would be related. They are not just arbitrary nonlinear functions. And if you consider the geometric case, then it turns out that magically all the diverging parts of these constants end up canceling out. Right? So you have actually a lot of terms appearing, but those that diverge in the same way, they diverge in the same way with prefactors that are exactly such that they actually cancel out. Okay? And so in this particular case, you have if you want in this picture, well, you have a subgroup, so there's a full group which somehow describes all of these constants. And then there's a subgroup of that group which happens to have the property that down here the action is trivial, it does nothing.
So there is one element.
Right? Well, no. So there's a large subgroup of the group up here, okay, which just has the property that the action onto this space down here is trivial. The action on this space is not trivial at all. Okay? And so what you can do in this particular case is it turns out you can verify that it's possible to renormalize things by acting just with that subgroup. Okay? And so that's the thing that then tells you that at the level of the equation you don't need to do anything. You can forget about this.
And so the problem that we had on this board, that you have a one-dimensional system of solution, disappears there. There should be one solution.
It depends. Well, yes and no. So no, because the thing is that if you want, you see, all it tells you is that for every way of regularizing this noise, you can find a sequence of elements in that specific subgroup which does nothing here, which allows you to renormalize things so that it converges to a limit. It doesn't tell you that this limit is the same, right? And so there is also a somewhat canonical way of renormalizing things which guarantees that the limit is always the same, but that canonical way of renormalizing thing doesn't fall into that subgroup. Right? So it shows that, so in general, if you want to guarantee that for two different ways of regularizing the noise, if you want to guarantee that you get the same limit, then you actually have to modify things here by some vector field which is of order 1, with constants that are actually of order 1 that don't diverge.
How do you diagram commutes there? Because if you say that downstairs the action of R is trivial on F.
No, so the action of some subgroup of R is trivial on F. Right? So I was saying that there's a large subgroup of R which acts trivially on F, and which is big enough in order to actually make things converge up here, but it's not big enough in order to make it converge to something which is always the same independently of how you regularize the noise here. Okay? Yeah, so it's subtle a bit. Okay. Right. Any other questions?
So may I ask the following? So you let me come to a simpler case with PyQ, yes?
Right.
So, but another question. So you consider square and cube, yes, and you consider this particular action of a group with minus C and minus EC. But does there exist certain axiomatic properties which the square and the cube must satisfy? Just in order to speak about this.
Yes. So here, no. Okay, so here in principle, you could have defined the square in any way you want, which has just nothing to do with the original V square, and that would give you an element of this space somehow. It would give you an element which is somehow no longer related, right? So it's no longer related to the original psi epsilon by lifting it canonically and acting on it with an element of just the real numbers, but it would still be a perfectly honest to God element of that space. It's just it doesn't have much of interpretations in anything. It does, okay, so there's a, so in general, you could obtain these kind of elements if you start to take approximations of your noise that are not themselves stationary. Right? So if you take your noise, which is stationary, it's just white noise, it's stationary, and instead of approximate it by simply mollifying some modifier, which then you automatically get something stationary, right? You start to make the shape of your modifier slightly depend on where you are or things like this. Right? So if you start to do this, well, then you pass to the limit. There can be situations in which you get a limit and the limit is just something completely different. It's not somehow, the limit would then not be the weak square of the approximations. All right, so if you start to take non-stationary approximations, but then you play around, you somehow square your non-stationary approximation and you just subtract. It might happen in some cases that you can still manage to simply subtract a constant in order to make it converge to something, but then there's no guarantee that that something is the canonical something which has as its covariance simply the square of the covariance of the original guy. So then you can basically get anything in the limit, and that's exactly what you were saying. So then you could get here something which is basically just totally unrelated to this guy here, but then it wouldn't really have much of a canonical meaning, right? So this is essentially just a, it's sort of an illustration of the fact that, it is simply the case that this map down here is terribly discontinuous, right? So if you just look at, there simply isn't continuity in the analytical sense. So you can always find some approximation so that this guy converges to anything you want, basically. Right? So it's not just that it's discontinuous in some points, it's sort of maximally discontinuous everywhere, in the sense that, you take any limiting guy here, you can approximate it by guys so that this here converges to anything you want. Right? So in that sense, it's totally discontinuous down here. And the only hope that you have of still building something sort of canonical here is by exploiting stationarity. Right? If you didn't exploit the stationarity of the noise, you'd be dead, basically, right? So you would have sort of silly statements along the lines of, okay, I can build things that converge to something, but I can make things converge to anything I want, and so there's, no good notion of solution anymore, and no nothing. Right? So the reason why here this construction gives you, right? So the point here is that you want to get, like a finite dimensional family of possible limits. Right? You don't want to get an infinite dimensional family of possible limits that are just parameterized by arbitrary functions, right? Because then it just doesn't make much sense anymore. Okay. Okay.
In the case of the KPZ equation, you told us that this group was just rescaling the height at which the interface was going. So how do we see in KPZ that we've got different possible limits?
So in that case, well, the different possible limits are simply parameterized by the vertical speed. Right? So in some sense, they are really not different because you can get them from each other by simply changing coordinates. Right? So in that sense, there's only one limit. Right? Yeah. Well, for example, here you really get a one-parameter limit, family of limits, and that parameter that's left can be interpreted basically as a kind of temperature, or sort of like distance from critical temperature. So.
And there is a kind of scaling, you take one solution, you reparameterize time or space, and you get the...
No, so here you don't, right? I mean, it's like if you take you cannot reparameterize somehow a supercritical, an Ising model with temperature above the critical temperature in order to get the one at temperature below the critical temperature, right? And that's exactly what you have here. Okay. Right, so let me keep this. Okay, so now, in some sense, we want two things now, right? So on the one hand, we want to have some sort of idea of how do you describe that space here, which is in some sense the space of all plausible interpretations of what these symbols are supposed to mean, or what are the functions that these symbols are supposed to represent. Okay, so in the same sense as here we had the sort of v square, v cube, and we had somehow this space was simply all triples, which we interpreted as squares and cubes, even though they weren't really squares or cubes, okay? So there's that thing. And then there's a kind of related question, which is the question of, how do you build that solution map down here, right? So in the phi cube case, well, we simply wrote the solution as a sum of two terms, and then we just derived the fixed point problem for the second term, and the first term was fixed somehow, right? And then there was no problem, so the space in which you set up a fixed point problem would be some space of continuous functions, maybe with some Hölder regularity, and there was no problem. So here, the space we would like to solve a fixed point problem basically in a space of things like that. Right? We want to basically, in this ansatz, well, essentially we just want to determine h, right? So that's the only thing we care about. All the rest here is just higher information about how we expect the solution to actually behave locally, right? Sort of to look like very locally around a given point, okay? So we really just care about h itself. But what we're going to do is we're actually going to set up a fixed point in a space of somehow completely general, you know, functions taking values in linear combinations of all of these 12 or 13 or whatever symbols, right? Which is just going to be set up in such a way that if something solves our fixed point problem, then it will be necessarily of this form for some h and some h prime, actually, right? So the h prime, so if you didn't have all of this bit here, if you had only these two guys here, right, then this would basically be like, you know, sort of, this guy would really be the derivative of that guy, and this would just be saying, well, near a given point, a function looks like its value plus its derivative times the corresponding, you know, linear first order Taylor monomial. Okay? So here we have a very natural kind of way of writing C alpha functions, right? So if I take a gamma, which is say between 1 and 2, then one way of writing the space, interpreting the space C gamma, is to say, well, H is in C gamma, an element of C gamma, I write it as H of Z equal to little h of Z times 1 plus H prime of Z times X. Okay. Without specifying that this guy is actually the derivative of this guy. Okay, so I just write it an element of C gamma for gamma between 1 and 2. I write it as somehow locally at every point Z, I have a Taylor polynomial of order of degree 1, which has its value and its derivative. But I don't care about the fact that a priori this guy will be the derivative of that guy, right? So these are simply two coefficients that are enough to determine a linear function or affine function. And so now I want a natural norm on these pairs, right? So what's the natural norm here? The natural norm is, well, if you want H to be C gamma, then H prime should be C gamma minus 1, right? So it's natural to impose that H prime of Z minus H prime of, say, Z0 is bounded by Z minus Z0 to the power gamma minus 1. Okay, and the norm is sort of the best constant here, locally. Okay? But then we want to impose something on H. Okay? And now the natural thing to do is to say, well, what does it mean to be C gamma? It means that if you look at H of Z and you compare it to its first order Taylor polynomial, which would be H of Z0 plus H prime of Z0 times Z minus Z0, right? So this, you want it to be for the Z minus Z0 to the gamma. Okay? Now, if you impose this, since gamma is bigger than 1, this actually forces H prime to be the derivative of H. Right? So you don't actually have to impose it yourself. You can say an element of C gamma, I just view it as a pair of functions, H prime, which I write in this way, which such that this norm is bounded. Okay, and if a pair of functions is such that this norm is bounded, then it's automatically true that this guy is the derivative of this one. I don't need to impose it, right? So it's sort of baked into the definition of my norm. Right? So that's a very natural way of writing the C gamma norm. Okay? Now, why, so here, why does this guy show up? Well, it shows up in the following way. You know, if I write as before, I write pi z of 1 to be just the constant pi z0 of 1 to be the constant function 1, and I write pi z0 of x to be the function, if you want, dot minus z0, or say z minus z0, so this is a function of z. Okay, so that's very natural. It's just the two terms that appear in a Taylor expansion, right? Then, so let me actually write a dot here. I don't want to write this as a z, because now what I see is that I actually also have a natural map. I have a map, say, gamma, depending on 2 points, say z and z0. Z and z0, okay, which have the property that if I want to change the value of z0 here, then that's the same as just taking some linear combinations of these symbols, right? So if I define this guy as the linear map that maps 1 to 1, and which maps x to x, and now I'm going to get the sign wrong. So I'm going to just basically choose a random sign, and then I'm going to adjust it as needed. So say z minus z0, 1, and there's a 50% chance that this sign is wrong, and we're going to see in a second. Okay, so if I define the gamma in the right way, then this has the property that pi z0 can be written as pi z composed with gamma z0, right? So it's obvious for the constant function 1 because it does nothing. And for, if I apply it to x, well, here if I apply gamma to x, I get this. And now if I apply pi z to this, I get dot minus z plus z minus z0 times 1, which gives me just dot minus z0, and so the sign was correct, actually. Okay? So if we define things in this way, we have this identity here. And of course, this operation, you can view it as simply the operation that takes the coefficients, right? It acts on a space of first-order Taylor polynomials, and it takes a Taylor polynomial which is interpreted as being a polynomial around the point z0, and turns it into the coefficients for the same polynomial, but viewed as a Taylor polynomial around the point z. Right? So all it does is somehow change the base point. It doesn't change the polynomial itself. Right? If you view this guy as the guy that somehow takes coefficient and spits out the corresponding Taylor polynomial. Okay? And so now, with this definition, I can actually rewrite this bit in a very compact way. Right? So first we have a natural degree again, right? So the degree here is 0, and the degree here is 1. Right? And now I claim that this norm that we built here is the same. I can rewrite it like this. I can simply compare, right? So h of z basically gives me the coefficients of a candidate Taylor expansion at around the point z. Okay? And now what this does is it basically just compares the Taylor expansions at z and the Taylor expansions at z naught. But of course, in order to compare them, you have to, you can't compare apples and oranges, right? So you can only compare them if you view both of them either as expansion around z or as expansions around z naught. It doesn't matter which one, but you have to pick one of them. Right? So the natural thing here is to compare h of z with gamma z naught, h of z naught. Okay? And now the claim here is that these two inequalities are simply, say, well, you take here the guy of degree alpha, And you want this to be bounded by z minus z naught to the power gamma minus alpha. Right? Because what would be the guy, if you apply gamma z z naught to h, what do you get? Right? Gamma z z naught, h of z naught, is given by, well, gamma applied to this does nothing, right? So it's just h of z naught times 1. And then you have h prime of z naught times x, but the gamma applied to x, it turns x into this x plus z minus z naught times 1, right? So here this is turned into this. Right? This is what the gamma does. Okay? And so now you see that if you compare h of z with h of z naught, well, if you compare the coefficients in front of x, you would just find h prime of z minus h prime of z naught, and you want this to be bounded by z minus z naught to the power gamma minus the degree of x, which was 1. And that's exactly this inequality here. Right? Whereas if I look at the coefficient in front of 1, then I'm comparing h of z with h of z naught plus h prime of z naught times z minus z naught. Okay? And I want this difference to be bounded by z minus z naught to the gamma minus 0. Right? And that's exactly what we had written here. Right? So these two inequalities here, I can write it in one go. I can write it like this. Okay? And you can convince yourself that this is the correct definition of C gamma for any gamma, right? So this works also if you go higher than 2, right? If you take gamma between 10 and 11, well, then here you just take something that goes up to order 11. And what properties do the gammas do? Well, the gamma turns out to be completely determined by these two identities to any order, provided that you furthermore impose that it's multiplicative. Right? So it's very natural to say that gamma, say z naught of a product of, say, A times B is gamma z naught of A times gamma z naught of B. Okay, so if you impose this, and you can, this is sort of natural, right? Because it just says that if you take two Taylor expansions and you multiply them, and then you re-expand them around a different point, it's the same as first re-expanding both of them around that point and then multiplying them. Right? So this is a very natural condition. And so if you impose this, then as soon as you have defined gamma on these two guys, well, then you have it defined on all products of xi's, right? So then you have a definition of these gammas on arbitrary polynomials and not just on polynomials of order 1. And then I claim that this actually gives you the correct definition of the Hölder spaces for any gamma by just taking it this norm. Okay?
Then you would need to define this gamma on stuff.
Exactly.
Like that.
That's the point. Right. So okay. So this is actually due to Whitney. I found that out sort of more recently. So Whitney, in the famous paper about Whitney's extension theorem, he actually defines the Hölder spaces like that. He doesn't use exactly the same notation, but he basically defines it like this. And so it turns out that in this, well, so now what I want to do is I want to do a more general framework. I want to say, well, instead of looking at just functions of this type here, I look at functions like that. Right? So I simply add all of these symbols here. Right, so I make a big space, which is sort of the vector space, which is all linear combinations of these symbols. And now I look at functions h that take values in that vector space. Okay? And now I want an analog of the definition of the space C gamma, which is a sort of direct analog for functions with values in these linear combinations. Okay? And the way I define it is I define it exactly like this. Okay, so I take exactly the same definition. So this definition here works in general. So it gives me a notion of C gamma spaces which are somehow not classical. Okay, so for any choice of, well, so what does it rely on, right? So it basically just relies on these gammas, it relies on these pi's. Well, the definition of the Holder spaces themselves doesn't rely on the pi's. Right? So in this definition here, I only have gamma appearing. The pi doesn't appear. But of course, the gamma was basically determined by the pi because it was the thing that makes this identity be true. Right? So that was essentially, in some sense, this identity was basically my definition of these gammas. Right? That's how I defined it. It was the thing that makes this identity be true. Okay? So that's how I defined the gammas. And then whenever I have a collection of these gammas acting on some vector space, that gives me a natural notion of Hölder continuities for functions with values in that vector space. Okay? And now the claim is that for all intents and purposes, these things behaves just like the usual C gamma spaces, even though an element of such a space might not represent a C gamma function at all. Right? It might represent a function which has much worse regularity. Yeah? So okay, so in our case, how do we define? How are these gammas defined, right? So, well, okay, so on the symbols 1 and x, they're defined in the same way as before, right? But now, how do I define it on this symbol, for example, right? Well, what did I have here? So here, remember, we said that the pi z of this symbol here, or say pi z naught of this symbol here, remember we actually defined it as the increment of this boldface pi, right? So we had the boldface pi, which was simply take the noise and convolve it with the heat kernel. And this guy was actually boldface pi of dot. We want minus the boldface pi of z naught. Right? So that's how we defined this guy here. Okay. And so, well, here now we have a natural, right? So this as a function of z is again times sort of 1. Right? It's constant as a function of z. It only depends on z naught. And this is, well, it's actually constant as a function of z naught, depends only on z. But in general, it doesn't necessarily need to be the case that it factors out like that. Right, so here, well, again, we know now how the gamma should act on this. It's basically whatever it takes to change this value here, right? And so it's something similar to before. So gamma, say z1, z0 of this would just be equal to the thing itself, and then plus, you know, the correct increment. And so here it would probably be this guy at z1 minus the same guy at z0, z1 minus this guy at z0 times the constant function 1. Right? So if I define the gamma like this, then that's very analogous, right? It's pretty much the same as here. If I define gamma like this, then this identity is still true for this symbol here. And it turns out now there is basically a unique way of defining the gamma, which has the following properties. Right? So there's a unique definition of the gamma such that the following are true. Well, so first we want it to do the right thing on polynomials, right? So such that first do the right thing on Taylor polynomials. Secondly, we wanted, well, on the noise itself is going to show up on the right-hand side of the equation, and there we wanted to do nothing. So that somehow gamma Z1, Z2 acting on the noise just gives me the noise back. So it does nothing on the noise. Then we want it to be multiplicative. Okay. And then the final property, and that's the important one, is that we want to have that pi z of anything of the form, something ending with a convolution. Okay. So this should be somehow related to the convolution itself. Okay. But then recentered in such a way that around the point z, this guy vanishes at the order given by the degree of this object. All right, so this should be true, plus a polynomial, an actual polynomial, a Taylor polynomial, of degree, the degree of this guy, such that pi z of this vanishes at z to the right order. Vanishes, okay, I'm running out of space here. Vanishes at z at the order given by this degree. Okay, so here you see, so like this guy is of degree plus a half. Right, so it was minus 3/2 plus 2, which is plus a half. And so we want this guy to be simply, so this object here would actually be heat kernel convolved with pi z of the noise, because pi z of the noise is just the noise, whatever the value of z is, because the gamma does nothing on the noise. Okay? So then this would just be this. And then what we do here is we subtract a polynomial of degree 1/2, which is just a constant. Okay, so the only polynomials of degree 1/2 are constants. And we subtract the constant that makes this guy vanish at z0. Okay? And so if this guy were of degree bigger than 1, we would have to subtract the polynomial of degree 1, which makes it vanish at order at least 1. Okay, etc. And so that polynomial is uniquely determined by the specification that you vanish at a degree which is actually higher than the degree of that polynomial. Right? So then there's no choice for the coefficients of that polynomial. Okay? So there can be at most one choice here. Okay? And so the claim is that these specifications completely determine both the gammas and the pi's. Okay? Because just by the recursive construction of these things, right? And there's a similar thing when you take a derivative of heat kernel, where you put derivative of heat kernel, same thing. Okay, so now we have essentially a complete specification of how the gammas are defined given the pi's, and the only thing that's missing somehow is that we don't necessarily know how the pi's act on products. Right? So nothing in this specification somehow tells us how the pi's act on product. It tells us how the gammas act on products, but it doesn't tell us how the pi's act on product. Okay? And so now the space, this space M, which I deleted, right, is basically just the space of all gammas and pi's, which satisfy, all of this specification. And so that furthermore, there's a natural norm on these things, right? And so the natural norm for the gammas is somehow related to somehow how close, right? So there's sort of you look at the matrix elements of this matrix, and the element that goes from an object of a certain degree to an object of a lower degree should be of order z minus z naught to the difference of the 2 degrees. And for the pi, there's a similar thing, which is you take a pi like this, you test it against the test function that's centered around the point z, and then you want this to behave like scale of the test function to the power degree of this object. Okay? And then the claim is that, well, first, the space is non-empty, which is not totally obvious. Okay? And for example, if you take like smooth functions and you lift it, then automatically d gamma that you build in this way does have these properties. So it does have these matrix elements that have the correct behavior. And so then this allows you to actually define this space M. Right? So now you have this space M, you have a space of Hölder functions corresponding to this space. Okay, and then actually you can build in this space, so in this space of Hölder functions, turns out now you can actually build a fixed point map which ends up being continuous. Okay, which gives you a solution of your problem. And now the whole problem becomes sort of the probabilistic problem, which is there a way of lifting noise to this space in such a way that it makes it converge, right? So I mean, can you build, what is this renormalization thing that acts on this space that makes things converge? And can you always make them converge? Okay, so I think I'll stop here for today. I'll see you tomorrow.